So hello, I'm Huang Zihan from School of Physics, Nankai University, and I'm going to represent our work about question 11, hail. There are 5 parts about our presentation: problem review, pre-experiment, theory, and experiment, and the conclusion. So let's go to the first part, problem review. So the question that extracts as much information as possible about the shape and dimensions of a metal container from the sound produced when dropping small objects into it. So from the question, we can know that it requires us to extract the geometric information of a container by the dropping sound, which means except for sound, any other information is not permitted. And however, however, try to imagine that if there are endless ideal microphones in the space, we can know how the sound waves are propagating or reflecting at any place and at any time. Certainly, we can know the geometric information of the container by looking for where the sound waves are reflected. But it is obviously unrealistic and meaningless. So I think the right way to solve this problem is to find some special points in the space. By detecting the sound information at this point, we can deduct some geometric information of the container. So also, it's unrealistic to find a method that can distinguish all kinds of word shapes and dimensions. So it is important to give a classification of kinds of shapes. First, we divided into irregular and regular shape. For the regular shape, it can be divided into pillar, a sphere, cube, and etc. Then the cylinder, quadrangular, and so on. So then it's part 2 per experiment. We choose some normal metal containers to measure their oscillogram. All of them were measured by dropping a small metal ball from the open end and detected by the microphone at the open end too. First is a small coffee can with 13.5 centimeters high, and secondly is a large thermos with 35 centimeters high, and the third a cup with 15 centimeters high. So from the oscillogram, we can see a periodical amplitude. This is bit phenomenon, just like the figure shows. It is a partial large figure of figure 1, the oscillogram of that small coffee can. And we find that the beat is much more obvious when the open end is smaller. To verify it, we set a comparison experiment. For a same container, we measure its oscillogram when the end was closed and open. And here is the result. So it's the attenuation of the closed end is slower, obviously. So here we preliminarily propose a possible way. That is, we choose the open end of the container as the special point, and the height is easy to determine. We can use free-fall time to detect it. Then for the pillar-shaped container, the sectional area can be determined by measuring how fast the energy loss. The slower loss corresponds to the smaller area, and the shape of its cross-section needs a measurement from its direction to determine whether it is isotropical. But what is the relation in quantity? So let's go part 3 theory. For a regular shaped pillar, we can use free-fall time to determine its height by measuring the time gap between you release the ball and receive the sound. That is an easy way, and the relation is presented as equation 2. For the sectional area of the container, or let's say the radius, it has relation to its open end and the reflective ratio as shown in the equations 3 and 4, connected by the open end impedance of sound. The meaning of some parameters are shown at the right place. So the further deduction, we get equation 6, which means as long as we measure the reflective ratio of the open end and the wavelength of the sound, we can deduct the radius, so the volume of the container too. Then I will show that how we realize it by a specific example that is part 4 experiment. So first step to determine it is a regular shape or not. We use Fourier transformation to analyze their ingredients of sound, and here's the result of spectrum. We can see that there are only one single frequency peak for a regular shaped pillar, about 534 hertz. Not difficult to know that it is the ancient frequency of the bottom of the container, right? And the irregular shaped pillar, however, owns many scattered peaks due to the uncertain collision of the mantle ball and the wall of the container. We know that if we hit different places of the container, it can produce sound with different frequencies. So step 2, for a regular shaped pillar, we can use free-fall time to determine its height. And here is the result. The H roller is the data measured by a ruler, just as reference. Sorry, maybe the slide is wrong. And step 3 is to measure its reflective ratio. We use microphone to detect the oscillogram at point A and B. One is below the open end and another one is above it. Then use the total energy flow through 2 points. We can know it is reflective ratio. Here is the attenuation has been considered and it can be selected. This is the oscillogram of point A and B. We can see that sound energy at point A is much bigger than the energy of point B. And we put this data into equation and get the reflective ratio equals to 0.997, and then we use the frequency spectrum we analyzed before. We get the wave vector k equals to 9.59, and also the shift phase. Then we get radius equals to 2.6 centimeters, and then the dimensions 300 cube centimeters too. So at the right place is a table comparing two ways to measure its dimensions, that is sound measuring and the ruler measuring. We can see that the arrow is acceptable. So let's go to part 5 conclusion. In our work, we propose a method to measure a container's geometric information by sound dropping a little object into it, and use the specific experiment to realize it and prove that our method can be used and the arrow is acceptable. For its shape, we roughly distinguish it is a regular shape or not. And for the regular shape, we proposed a method to measure its dimension. Still, it can be divided into more circumstances, like how about it? What if it is not a pillar like a cube or a sphere? As for the regular shape, we didn't go deep to find that it is a cylinder or a triangular or something else. Due to the lack of experiment devices, sorry. But I think that this can all be solved by adding more microphones, as I mentioned before. And so I think this is easy to realize. So, and that's all. Thank you.
Hi, I'm Alexander, and I will be the opposing team for problem number 10 for Team Slovenia. So the official problem statement of this problem, the official problem statement of this problem says that we should extract as much information about the shape and dimensions of the container from the sound produced when dropping small objects into it. Here it's important that we only use information of the sound of the object, in my opinion, and extract the information from there. So in the presenter's presentation, he classified objects into different kinds of shapes, into irregular and regular, and cylindrical geometries and rectangular geometries. but it would have been better if he also clarified where the border exactly is between regular and irregular. Next, he used, from the properties of the sound, he used the amplitude that comes from the reflection of the sound, and he used the covering a covered and uncovered end to get the different impedances of the object, so as to extract the information. He also had the spectrum and Fourier transform with only one peak of the sound. Here it could maybe be an improvement if different measurements of the Fourier spectrum can be used to clarify that it is only one peak in the Fourier transform and not multiple peaks. He had the theoretical argument for the impedances, and he also used the falling of the metal ball itself to get the height of the container. I would think that this point would maybe be in conflict with using only the sound of the container, because he's also using the timing of the dropped ball and the position of it. Yes, from his presentation, I would say that the frequency was underutilized of finding what the shape and dimensions are. And he did classify the different kinds of containers, but the only experiments they had were with cylindrical containers. Something to improve would be to get different containers and check their method and their experiment with the different containers. And they extracted the size of the containers from the impedances and from the dropping of the ball. I would say that the perpendicular dimensions were extracted fine, and again, the ball was maybe straying from the problem statement. I would like to discuss with the opponent, with the presenter, whether they did any kind of blind experiment where the experimenter only had the sound information and tried to guess the properties from there, or if they just did an experiment where the experimenter already knew the size, because this can bias the experiment. And did they consider oscillations of the sides if they are induced, and oscillations of the volume, or only oscillations of the bottom? Yes, thank you for your attention.
So for your first advice, I hear that you advised me to use different Fourier transformation, and in fact, I didn't know what you mean for different Fourier transformation.
No, I meant just recording the sound from different at different points in the setup, and try to see what kind of frequencies appear in the spectrum. Is it only one always, or do different oscillations arise?
Oh, okay. And for your next question, I think the conflict of timing is inevitable, because when you measure is wave figure, or what's called oscillogram, there is also time information on it. So I don't know what if you really didn't consider the time and you don't allow us to measure it. So I don't know what you have better advice about how we get the size information or geometry.
Well, I can't share what I did, but
okay. So So I think yeah, we consider we considered this problem before,
And
but we think this is
what about a blind experiment? Did the experimenter always know the shape before trying to guess it or determine the dimensions?
okay. Okay, this question that we first for the for the slides I said that we first classify our shapes and dimensions of some containers because we think a totally blind experiment we can't achieve that. But for a totally black box or a blind experiment, we can't just use a dropping ball to measure it. So we just roughly classify it, and we can find a method to judge which is what we want. And
Okay, so would you say that the question's answer is that you can determine the shape or and dimensions, or no?
just if we classify some special or determine the shape, we can. But for a totally black box, we can't. We didn't achieve that.
Mm-hmm. Okay, so I guess this comes back to your classification of regular and irregular. What exactly, where does the boundary between those two lie?
This is yeah, this is a vague concept.
Mm-hmm.
So my opinion is that if there are too much.
So, for example, if you could assume that the shape of the object was in some sense regular, like some cylinder or some rectangular geometry or something, then would a blind experiment, assuming that, be able to determine the sizes?
That is the question, right? We didn't find a method to achieve that.
Mm-hmm.
Yeah.
And again, with the Fourier spectrum, do you think that higher peaks could appear in the Fourier spectrum?
Higher peaks.
I mean, at higher frequencies.
Okay, we use the for a certain container, there is no higher frequency. Yeah, this is our experiment with that. Okay, for your earlier question is that we think that I have said that if there are endless microphones in the space, we can measure any size and geometric information, but yeah, it is unrealistic.
So the reporter, still, I wasn't quite satisfied with the regular irregular classification of the reporter. I would like to maybe discuss about seemingly regular but as well irregular shapes such as stars, polyhedrons. Where does the reporter think that would fall in their spectrum analysis? So polyhedrons, up to which polyhedron is it regular? Can you make star shapes? What makes it exactly regular?
Okay, can you hear me? Can you hear me?
Yep.
Okay. This is that why a irregular shape has many peaks, because when I drop the metal ball leisurely, it may hit a different place of the container. So if I drop many times or I drop it collision with the one side and it move to another side, it may form many peaks. For you mentioned a star shape or something else seems irregular, but a regular shape. I think we can just drop the metal ball in a special point, and we don't change this place. Just for maybe maybe it won't form so many peaks, and we can use this to justify whether it is regular or irregular.
So do you think you could extract any information if you drop the ball at a random point in the container?
No, I think I think we must choose a special point, just or two or three. Just it must be limited. And
what about if you assume that the geometry is regular and you drop it at a random point?
Is that we drop it at a different place of the end at the open end.
Mm-hmm.
So it may just it may not just fall to the bottom of the container. We can
It may be experimentally difficult, but theoretically you could.
Theoretically,
I mean, expect theoretically, would you be able to extract any information?
With the perfect.
So I don't think so. So for the theoretical, I don't think so. We can extract any information.
Mm-hmm.
Because usually when you drop a ball and you have a certain spectrum of a container, this spectrum contains information about the length scales of the container from resonances and so on, which would perhaps give you some information at least. Not nothing, as you said.
Oh, right. This is actually, in fact, yeah, right, is a possible way, because but you have to consider more, because not only its shape and the dimension influence its frequency, also its material, what type of material, and maybe you can't just distinguish. Maybe you can distinguish that the influence is caused by the material or just the shape. So I think it may be possible, but it's really a hard way.
You could also you have when you look at the spectrum, you also have not only oscillations of the container, but you also have other oscillations, like for example the air. Could that give you information?
No, I think that the case of the air oscillation is not so important, because this is a pulse wave, and the frequency is mainly determined by the bottom of by the collision with the from the bottom and the mantle ball. So in this case, the air is just a deliver.
Could you please specify under which assumption will the technique proposed by the reporter work? And do you consider this assumption enough to the condition of the problem? First one would be the opponent and then the reporter.
I would think that the reporter has to have access to the container, so to be able to specifically impose the condition of open and closed end and of dropping the ball right in the center, and it couldn't do it for a general sound.
Oh, okay. What about how will respond the reporter? Under which assumptions will your technique work, or is your technique working?
I think our work is really useful when we can when you tell me the classification of the shape. Just like in our special experiment, we just the classification to irregular or regular, and we just do the regular shape, the cylinder. So if you don't give me a classification of limited shape and of the container, so we can't find a general solution. Yeah.
But is the material important?
Well, I'm sorry. Yeah, we have a raised hand from the Klim. Klim, you're welcome.
The question for the reporter, for how many containers you have compared the theoretical results that you've measured with the ruler and so on, and the results obtained by your method? How many containers?
Mainly we did the same just about the similar containers, but
how many? How many? 1, 2, 3?
If you didn't consider,
I've seen one on slide number 25 for cylinder. How many containers there were overall?
2.
2 of them.
If we consider regular or irregular, maybe 4. They are both classified to regular and irregular.
Okay, thank you. I also would like to ask the reporter that your theory, as I understood, depends strongly on the reflectability of the material. And is the material important, and how have you checked this? Which assumptions about the container material did you make?
Yeah. Okay, got it. We have considered the material because our theory has included the wavelength or frequency of the wave. So for a certain frequency of the sound, we can use it to determine the impedance of the open end, or just and then use it to determine its area, sectional area, size. So no matter what kind of materials you use, you can use Fourier transformation to get its frequency, right?
But can I imagine a material that is not reflecting any sound waves? For example, very rough metal.
We didn't consider whether what if it will be if it is not a mantle container, because the question asks us to do the mantle condition.
Okay, thank you.
Okay.